Once again, my name is Gerald, and I work for Park Systems. We are an atomic force microscopy company that is based out of Santa Clara, California. And thank you very much again for taking time out of your morning, afternoon, or night, depending on where you're connecting from around the world. Here we have Professor Rigoberto Advincula, who will be giving a presentation on molecular imprinted polymer films.
So good morning, good evening, good afternoon, whatever time zone you are in. My name is Rigoberto Advincula. I'm a professor at Case Western Reserve University, and I'm glad you can join us for today's webinar. And this is my group. We are a materials research group at Case. I belong to the macromolecular science engineering department. We publish a lot in the areas of nanostructured materials, interface, new polymer synthesis, and applications as well. So this particular slide shows that the interdisciplinary nature of nanotechnology allows us to utilize different aspects of each scientific field in order to harness the applications that are originating from the nanoscale and nanoscale phenomena. And that means this is naturally a cross between what we know is our bio-inspired systems or biological systems, soft matter, polymeric materials, even inorganic or carbon-based materials. That means that you can link this up towards functions such as electronics, display materials, and sensors. On the other hand, our group really does a lot of work as well on biomedical related research, whether it be functionalization of surfaces for bioimplant and fibroblast cell growth, utilization of antimicrobial agents and coatings using graphene-based materials, or investigation of DNA, micro and nanostructuring, and even the use of surface plasmon resonance spectroscopy. So the talk today that I will give on molecularly imprinted polymers is basically a bio-inspired system that allows us to harness material systems that can be used for sensing. So a typical sensor design is based on a recognition element, a chemical or biorecognition element, which is part of a system that comprises that of a transducer element and a signal output, and then finally a readout. So what you can see here is, for example, if we're dealing with chemical analytes that are very specifically detected sensitively and selectively on this chemical recognition element, that will result in a change or response either by light, magnetic, electric field, chemical potential, that is then translated to a signal, preferably an electrical signal, for example, or a digital readout, or it can actually be an optical signal that can be detected by the naked eye, which then gives a particular response. And that response can be quantitatively measured, for example, or even a simple yes or no. So this is a very basic sensor design. Now what I'm going to talk about today is the advantages and perhaps even the nuances of applying what we call molecular imprinting. As you know much more later, molecular imprinting basically is taking an analyte as a template or imprinted model such that the pattern or the cavity produced by the imprint can then be used to sensitively detect that analyte in future sensor applications. So for example, as a film or as a monolith, meaning a solid block, the film or the monolith can be attached to a transducer surface, whether it's an electrode surface, a fiber optic, a quartz crystal microbalance, or in the form of colloidal particle or solid particles. The response can then be detected as a change in electrochemical signal, optical signal, acoustic wave, or even by detecting the change in fluorescence of absorbance of material. In fact, not only polymers are used for molecular imprinting, one can utilize nanoparticles or even other types of electropolymerizable monomers, which I'm going to demonstrate more for today in terms of constructing this biorecognition element. So the term molecular imprinting, which probably attracted you to sign up for the webinar, basically is a method of making a highly sensitive or selective recognition element that can be utilized either for sensing or for separation. Now in our case, today we will just focus on sensing, although a number of potential applications and even commercial products to date have been demonstrated for separation. The idea of using it for sensing has been around for a while, but really there's a criterion by which several criteria, parts of a sensor design that has to be met in order for a successful application to reach the market. So for example, one is interested in portable sensors or sensors that can be highly sensitive or selective based on a biochip or lab-in-a-chip design. In other words, if you have a sample of blood or a sample of saliva or any other sample which requires you to remove the matrix or purify it or concentrate the analyte, this has to be done or undergo through a separation method. Hence, the lab-in-a-chip means that all of this function is done in a miniaturized level. Such is the case for most analytes. The analytes, ideally, if they can be detected without sample preparation, is the most preferred case. However, in reality, most analytes have to be separated from other competing analytes, other matrices that can cloud the behavior of the sensor, or simply to enhance the signal-to-noise ratio that one can achieve with a particular sensing experiment. Our group actually has pioneered a lot of methods on surface plasmon resonance spectroscopy. Surface plasmon resonance spectroscopy, we will have some time to go over it in this seminar, is basically a method by which we harness the surface plasmon polaritons present on a gold surface. Another term you might have heard in the past is called surface plasmon or plasmonics. This is related to the presence of surface light or surface polaritons based on a noble metal surface such as gold that then causes a channeling of the reflectivity towards an evanescent wave mode that can either be propagated on a surface through what we call an ATR experiment or through a scattered mode in a particular mean-scattering phenomenon that is present in particles. Hence, plasmonics is closely related to SPR, except that in a spectroscopy mode, you can actually measure them with techniques such as this ATR. And basically, you will see a number of applications where we've utilized SPR to evaluate the performance of molecular imprinted materials. But before we go to SPR, let us review and focus on some possible uses of a macromolecule called a dendrimer for designing molecularly imprinted films. So in this picture, I'm just focusing on a dangerous substance called chemical warfare agent, which has many classifications, but this includes sarin, soman. These are banned substances, obviously, and quite toxic. For example, it takes about 200 milligrams of sarin per cubic meter to cause death within a couple of minutes. In other words, it's very toxic and also dangerous in the hands of the wrong people. However, we're interested with it, and obviously we cannot test the real thing. We have to utilize an analog. And we use methylphosphonic acid and pinacoyl methylphosphonate as a soman analog for all our tests. So in this case, we actually designed a dendrimeric material, modified it with copper chloride, and at the same time added an electropolymerizable carbazole group. PAMAM, or polyamidoamine, is commercially available dendrimer. When we load it up with copper and functionalize it through the imine with the carbazole unit, we render this molecule or macromolecule to be electrochemically active. So the idea is to pin this film on an SPR chip, introduce the active or analyte agent, and then use the SPR experiment to sensitively detect the presence of, let's say, the model summon or nerve gas agents such as PMP. So the procedure is as follows. Here you can see the dendrimer was modified with carbazole reactive groups, then doped with copper or impregnated with copper. The idea is that copper actually helps in complexing the analyte on the surface of the dendrimer, and then electropolymerize the dendrimer on top of an SPR chip or gold surface. We did several variations. One is we simply spin coated the material and then electrochemically crossing them on the surface. The other is we actually modified the surface of gold with a carbazole unit that is then used to electropolymerize and complex with the dendrimer, leading to two types. One is an electropolymerized sample without copper, and another one with copper. And you'll see later the differences on these measurements. So for example, in terms of efficacy, the initial experiments we did was to look at the reflectivity response as a function of concentration. So SPR sensograms shows that we can detect up to 10 to the -9 molar or nanomolar sensitivity. That is, with the copper containing material, we get to the limit of 10 to the -9 molar. However, without the copper, it only reaches up to the 10 to the -7 molar. So clearly, the presence of copper enhances the sensitivity or detection limit for the analyte. In fact, the modification of the analyte and its presence on the surface actually changes the contact angle or wetting of the surface. We did this verification with potentiometry, and it showed the same result, that the presence of copper enhanced the detection limit up to 10 to the -9 molar. So we hence use this procedure for all our tests. Another is that of selectivity. So for example, if we take the PMP, which is this, we try to detect EMP, which is not very far from PMP, we observe a similar response or closer to PMP. However, if we use DEP, acetic acid, or sodium phosphate, the response is low. In other words, this system we built is quite particular with PMP and EMP. And so if we test it with vinegar or any inorganic phosphate, it doesn't show a good response. So the selectivity test actually shows that it's quite selective for PMP, and it's closer analog called EMP. In fact, the breakdown product of PMP is actually methylphosphonic acid. When we try to detect the breakdown product of PMP, we were able to reach up to picomolar level, or 10 to the -12. So the highest sensitivity can actually be observed with this system. Now, mind you, all these interesting results, we are working with a non-molecularly imprinted material. In other words, what if the system was actually designed to have a molecularly imprinted system from the ground up, and what would be the comparable performance? So let me describe the possibilities here. Let's talk about enzymes. Enzymes, receptors, these are functions in the human body or living systems, if you will, that are basically made up of proteins, which can be activated by the presence of a substrate. Different types of models can be visualized in terms of an enzyme action. One is the rate model. The other is the occupational model. And the third one is the induced fit model. Either way, it requires the presence of an active site where the analyte or the substrate is bound to the surface into the cavity, quote unquote, and this either elicits a change or a lowering of the activation energy or a particular catalytic response. That means that you have to have some specificity in these interactions, and there has to be an advantage in terms of the signal that is generated upon this synergistic interaction. Now, in the lower part, I show here a comparison of a dendrimeric size, which is basically a hyperbranch polymer or macromolecule, in which the generation or the size goes from G3 to G7. So exponentially, you can see the increase in the size and the amount of functional groups as you grow a dendrimer step by step into a larger macromolecule. Now compare that with proteins such as insulin, cytochrome C, histone, hemoglobin. What I'm trying to point here is that dendrimers or artificial enzymes or receptors can have a size dimension comparable to macromolecules or large molecules that are hyperbranch in nature. We're actually talking here about anywhere from 1 to 4 nanometers in diameter or size, which is the size of proteins as well, as you can see here. So what happens is these proteins can either be part of a membrane system or can be part of cells and tissues in general, in which the presence of your analyte allows it to either transport or, again, produce a particular catalytic effect, such as NADH, NAD, or other types of conversion that's happening with molecules in the body. By the way, receptors or enzymes are designed to work all the time. And the reason we have diseases is when these enzymes are gone awry or are not working properly. Now, the concept here of molecular imprinting starts basically with mimicking this lock and key mechanism of an enzyme. Now, we usually think that we need a key to open a lock. In molecular imprinting, it's the reverse. You have the key, but you don't have the lock. That means that you need to design a lock from the bottom up in order to accommodate a particular key. So the next illustration here shows how this works. Basically, an analyte is a key. Monomers are used to complex with the key. These particular monomers, together with a cross-linker, can be polymerized such that it forms a cavity or it forms a new cross-link polymeric system that surrounds the analyte. And then by removing the analyte or the template, you are left with a cavity or interaction that is very specific to the size, shape of the original analyte. In other words, there's a binding event or there's a release event that can occur between the two as a matter of equilibria in such that this binding event can be detected. So another picture here is, for example, analytes that are present in this molecularly imprinted cavity, and the interaction is synergistic such that the presence of the non-covalent interactions together with the analyte is a good fit for that exact analyte that was the original template. So molecular imprinting basically is a templating approach for making an artificial receptor or sensor that basically is exact for the key that is being used. Now, here, the molecular imprinting approach is further carried into a type of non-covalent complexing mode, such that this protoenzyme or pre-polymerized complex is actually similar to a large macromolecule. So the way we visualize this type of interaction is basically an analyte which can be surrounded by a peripheral group of monomers. Or in our case, we are actually trying to look for what we call hyperbranch monomers or dendrimers that can be used to surround the analyte. So once you do that, you can then polymerize this complex and end up with a cavity that is, again, very specific for this template. So removal of the template is very important because this cavity then allows you to sense future events in which the analyte is present either from a sample solution, a test solution, or even an unknown where you want to detect the presence of that analyte. And in this case, since I introduced earlier SPR, we are basically putting this molecularly imprinted film on top of a gold electrode, which we can then do the surface plasmon resonance spectroscopy studies. Now, SPR really is just but one transducer element. You either can use electrochemical impedance spectroscopy, fluorescence spectroscopy, quartz crystal microbalance to basically sense the presence or absence of the template or analyte together with the molecularly imprinted film. Okay, here I'm showing you some of the drugs that we first investigated using this approach. The monomer we utilize in this picture is basically a tertiopene monomer, which is capable of hydrogen bonding with theophylline. In this case, we can do theophylline, theobromine, caffeine, paracetamol. So you can imagine that each of these analytes can be specifically made as a molecularly imprinted polymer film on top of this gold electrode. In other words, not only theophylline as illustrated here, we can have a sensor for theophylline, a sensor for theobromine, a sensor for caffeine, paracetamol, and naproxen, and so on. And that will be very specific to this template that was used, which I'll show you in the next few slides. Here is a survey of the different monomers we used, from tertiopene to bifunctional tertiopene to bifunctional carbazole, and that's shown here. We can even have a second generation carbazole dendron. And once we electropolymerize them, basically the cyclic voltammogram here shows that they can be cross-linked on the surface as robust films. And the conducting polymer, if you are not familiar with it, basically is a monomer that can be electropolymerized, and once polymerized, it can have either fluorescence or electrical conductivity as part of the pi delocalization and charge carrier generation on this type of polymer. So this is very different if you're familiar with the E-MIP field. Most of what has been reported in literature are based on acrylate, vinylic, styrenic type of polymerization reactions. In our case, our reactions are based on electropolymerization or anodic polymerization through the reactive electroactive monomers. Again, here's another picture of how it is done. The thing that we add in terms of increasing the efficacy of these systems is basically modeling it in terms of non-covalent interactions. Non-covalent interactions means that we optimize the ratio of the monomers that are used for a particular analyte. In this case, you can see a 2-to-1 ratio that has been optimized using semi-empirical ab initio methods or calculations to generate the most stable conformation as well as the most stable pairing for the analyte and the monomer. Going a little faster here, what we have is basically the procedure that was used on using an SPR chip or sensor. Basically, we templated it, polymerize it, and then remove the template. So we are left with cavities on the film, which when exposed to the particular analytes in solution, will then complex with the analyte on the cavities. Okay. Let me skip this part. This simply shows how the monolith was made electrochemically. Okay. So we did some optimization studies. Looking at this graph, the monofunctional monomer was washed with acetonitrile. And we found that by washing it with acetonitrile and at the same time applying a constant potential of 0.4 volts, actually produce the biggest response on the SPR curve. Also, we compared between a bifunctional and a monofunctional monomer. In general, the bifunctional monomer is a superior design compared to the monofunctional units. So with this optimized system, here you can see how we made very selective sensors based on the template that we use. So what this means is that if naproxen was imprinted, the rest of the analytes did not bind to it. If theophylline was imprinted, the rest of the analytes did not bind to it. And then finally, the paracetamol, the rest of the analytes did not bind to it. So what this tells you is that we can make custom-made or made-to-order films based on the original template that we use and achieving very high selectivity simply because the exact shape or cavity that's specific for the original analyte use works very well or distinguishes it from the other analytes. Sensitivity and stability are demonstrated by these two plots. Sensitivity is showing a limit of detection up to 3.36 micromolar, limit of quantification about 11.2 micromolar. What is important here is to show that we have a linear calibration based on concentration. On the right hand, you have the stability of the detection that was done even up to 45 days. In other words, we only see a 15% reduction on the sensitivity and selectivity even after 45 days. Actually, the other experiments we have done in conjunction with this are, of course, selectivity measurements and also stability measurements, and then finally repeatability. Or in other words, these sensors can actually be reused by washing and then reusing it again and again up to several cycles, which I don't have here. Now going forward, just showing you that molecular imprinting is not a aberration or it works very well, is that we can molecularly imprint virtually any chemical of our choosing. In this case, we demonstrated with folic acid. Folic acid here can be electropolymerized together with the bifunctional tertulfine monomer on a quartz crystal microvalent surface, and we can detect the molecule. Okay, this is just a general methodology of the process. The optimization for electropolymerization by monitoring the cyclic voltammogram as well as the quartz crystal microvalent trace. So you can see here pretty much we have a linear deposition process. Here you have the monitoring of resistance versus the imprinted or the control polymer. Now, the control simply means that we did not do any molecular imprinting, but simply polymerize the polymer and then try to do sensor measurements. And here, the complexation ratio for the monomer and the monomers and the analyte is actually 3:1, as shown in this molecular modeling diagram. Now let me focus then on the value of atomic force microscopy. Now atomic force microscopy is one of the characterization methods that we use. In fact, it's quite interesting and invaluable in that it gives us a morphology differentiation between films that are printed, imprinted, sensed, and washed. And that means that we can monitor the changes in this morphology, not necessarily observing any changes in porosity, but that each type of film has a particular morphology that is quite important in terms of improving its efficiency. In fact, in some cases, we've seen the increase in porosity by certain treatment procedures that can visualize directly by atomic force microscopy or AFM. Now, We then try to demonstrate this and compare it with other analytes. So for example, first of all, the imprinted is superior to the non-imprinted. The frequency shift of the imprinted, meaning higher signal-to-noise ratio, was observed with the imprinted versus the control. And then we try to compare the performance of this sensor based on folic acid between stearoic acid, caffeine, and theophylline. So obviously the highest response was found on the originally templated molecule. Okay, and this was published back in 2011 with ACS Applied Materials, and in fact made cover page for the journal as shown here. Now, some other molecules we investigated. Trichloroanisole is actually a common substance. If you drink wine, if you're familiar with the wine industry, this is basically bad wine. Whenever you have a high level of trichloroanisole, basically your wine has a bad taste or maybe worthless. So designing a sensor to detect the levels of TCA in alcohol is an important objective in this work. And again, we employ the same tools. We did the modeling. In this case, we actually use a co-monomer modeled with the template molecule TCA. We optimize the deposition by looking at the cyclic voltammogram as well as the quartz crystal microbalance trace. What we demonstrated is that you have high sensitivity and selectivity, including the optimized films between the molecularly imprinted and the non-imprinted polymer. And here you can see that the MIP, okay, has good binding characteristics compared to the NIP. Okay, and so the performance of the sensor again was validated by this sensitivity and selectivity techniques. Now we are on to our last few topics here. What I'm showing you are colloidal patterned surfaces based on particles where we can deposit or electrodeposit a conducting polymer around it. That means that we can create conductive polymer patterns of a high surface area or accessibility to an analyte compared to a flat film. So we dramatically increase the surface to volume ratio advantage by doing this patterning. This was actually demonstrated on several fronts. But here we refer to the use of these patterned surfaces for distinguishing the chirality between norepinephrine analogs. So this diastereomer or enantiomer can be distinguished based on, let's say, the left or right hand of the molecule. Of course, a common mixture of equivalent amount will be a racemic mixture. But we are interested only in norepinephrine, which is effective as a drug. The other, which is the mirror image of this drug, is not effective. So how do we distinguish this? Well, we employed, again, quartz crystal microbalance and templated or molecularly imprinted our way towards the detection of the right norepinephrine stereoisomer. We utilize this arrayed film as shown here. The idea is once we molecularly imprint the naproxen, it will create cavities along this film, and as you can see, we should have an increase in the surface area that's exposed to the analyte and the film. And then, of course, a layer that functions as your transducer system. So we did several tests. We optimized it. We first demonstrated selectivity. So if we imprinted norepinephrine, it did not detect, or it has a superior signal-to-noise ratio and higher frequency detection for the original template as compared to the analog and dopamine or naproxen. Here it shows the value of optimizing the film by potential washing. Here it shows that we have very good chiral selectivity. If we template it originally with one enantiomer, we get good response. On the other hand, if we template it with the opposite enantiomer, we get a good response of the opposite enantiomer as well. Here, MIP was demonstrated between the non-arrayed and arrayed sample, and here between the MIP and the NIP. So MIP here shows that you have the higher frequency response. Now, since then, we've actually demonstrated this to many other molecules, from dopamine to DNT to bisphenol A to melamine. This really works, and it's a very important gateway for applying molecular imprinted films to our sensors. Almost done. This is actually my last slide. So where do we go from here? Well, we are continually doing more experiments with other types of analytes, but the next frontier for us, actually, believe it or not, is utilizing viruses. These plant viruses are relatively harmless, non-carcinogenic. They're non-toxic as well. And what we intend to do is to carry out molecular imprinting on this plant viruses, either utilize this as monomer films or arrays, or utilize the functional groups on the surface and functionalize it towards molecular imprinting. And I can talk more about this if given another hour, but I have to end almost at this point. So anyway, with that, I'll be ending my webinar presentation here, and we'll be happy to take any questions from the audience.
Just to avoid some dead air here while you guys are thinking and writing some questions into us, I'd like to let all of you guys know, it looks like our marketing team at Park Systems in Korea has finally started uploading previous talks from Professor Advincula. So if you're interested in any of the other lectures that he's given over the last couple of months, they are now available at parkafm.com if you go to the previous lectures under the Nano Academy section there. We've featured talks on topics such as nanomaterials for the oil and gas industry. We've taken a look at graphene. So the topics are going to be changing from topic to topic, from field to field every month or so. So keep an eye out on parkafm.com. We'll also be, of course, sending out emails and making calls as well, like we have been. But there should be a new lecture to look forward to every month or so. In addition to that, I believe our next talk next month, September, it should be around the second week or so. So keep an eye out for invitations and more information on that to be posted as well. They're going to be hosted all here on GoToWebinar. Any closing words and thoughts, Professor?
Well, I'd be happy to answer any further questions either by email through you or through me directly, which is rca41@case.edu. And again, I'd like to thank Park AFM Systems for this opportunity to present a series of these webinars. And I hope it has been helpful to our audience and, of course, to our future audience. So with that, I'd like to thank you and enjoy your day.